Now we have our next keynote speaker, who's also talking about a very similar related topic. It's Tim Brent, which is an associate professor in the Cheriton School of Computer Science at the University of Waterloo. He has previously held research positions at Netflix, IBM's Center for Advanced Research Studies, Hewlett-Packard Labs, and EPFL. His research interests include empirically evaluating, understanding, and improving the performance of computer systems and networks, parallel and distributed systems, operating systems, and developing systems and devices to better support the Internet of Things. So, Tim, please go ahead. I think you're muted.
Let's try that again. Right. So thanks very much to the organizers for actually making this happen and for the invitation to speak, and for everybody who's showing up today. It's really nice. So the title of my talk is Conducting Credible Performance Evaluations in Environments with Highly Variable Performance. And as I was creating this talk, I realized that much of what I'm talking about really isn't just a problem when the variability is high. So this was the title I wish I had used. So conducting, getting rid of highly variable. It's really not. And then as I continued working on the talk, I realized that, well, I should be pointing out that empirical performance evaluations are always variable. So then I wished I'd used this title instead. So what I'm going to talk about is I'm going to describe some problems people encounter. A lot of this talk is going to be a repeat of what Robert had just talked about, right? Problems people encounter when running experiments in environments where performance results are variable. I'm going to use some examples from environments with high variability, including Wi-Fi networks and cloud computing environments. I'm going to focus really on the kind of evaluations where you're comparing results of different algorithms or different techniques or different alternatives, and talk about some of the problems that can occur and how to avoid them. So this talk is based on work with Ali Abedi and Andrew Hurd, and it's the stuff I'm focusing on here is out of papers that we published in Operating System Review in 2015 and in ICPE in 2017. So our motivation was Wi-Fi networking. So we'd been doing work in Wi-Fi networking. We'd seen performance evaluations that we didn't really believe. And when we started to try to conduct empirical evaluations of Wi-Fi networks, we found that it was very difficult. So I'm showing here a graph. On the x-axis is time, and on the y-axis is throughput. So we're continuing to measure throughput every 60 minutes, or sorry, we're computing the average throughput over a 60-minute interval, and we just plot that over time. So the reason I like Wi-Fi networking as an example of a variable environment is that people agree that it's variable. There's just no question. There's no doubt. It's variable, and you can't see when it's happening. You don't know when it's happening. There could be a microwave. There could be somebody else. It could be movement in the room. And so one of the issues is that we have to consider, how do we conduct experiments in this kind of environment? So after we worked on, and so a lot of the stuff I'm going to talk about came about from the results of working on Wi-Fi throughput. And after working on solutions to this problem, we also wondered if this could be a potential problem in cloud computing environments. And so that led us to do some looking into cloud computing environments. So lots of variability. You don't know when it's happening. You can't predict it. And what do we do about it? So in the cloud computing environment, our initial paper, we were able to get some data, some actual data that was collected by others, Shad et al. In 2010. And this is plotting on the x-axis time, so running this experiment over and over and over again. And this is a benchmark score, right? So higher is better. And this is just showing how much variability there is running the CPU benchmark on Amazon EC2. They ran it every hour for 1 month. And this is the kind of variability they saw, right? So sources of variability, well, you're not always running on the same machine. There's two bands, the upper band and the lower band. I guess those are two different CPU instances, Opteron versus Xeon processors. And then there are bands within each band, right? So variability within each band, sorry. And that's due to multiple VMs on the same physical machine, right? So So part of the problem might be that cloud providers have been claiming performance isolation and people seem to actually believe them when the reality is that it's just not true. And then the other, maybe more important thing is that to recognize that they haven't really designed cloud computing environments for conducting these type of experiments. We're just, as researchers, we find them convenient and inexpensive and a way to access many more machines than we can typically access. So I want to remind people, this is running exactly the same benchmark over and over and over again, and look at the variation in those results. Right? And variability continues to be present. Robert just talked about a whole bunch of evaluations they did. There's variation in CPU, memory, disk, network, and importantly, application performance, right? So these things have big impacts across the board. So why is variability a problem? Well, from our perspective, right, we were in the game of, we want to compare techniques. We've invented a new technique that we think is better, faster, and we want to try to demonstrate that. So imagine you have a technique A, a technique B, and a technique C. A and B already exist, and C is our brand new shiny approach that we're all excited about, right? We're hoping it's faster, and we obtain and report some measurements that indicate C is faster. The problem here is there's a fundamentally important question is C actually faster, or is it possible that the environment changed in a way that C now produces measurements that look faster, right? And so in other words, the question we want to know is, are these findings credible? So the problem I'm going to talk about today is, the credibility of a performance evaluation, right? So one question is, how can you tell if the performance evaluation is credible as a scientist who's conducting the research, or as a paper reader or a reviewer of the paper? So I think, one of the things that we thought about when we started to try to evaluate performance by doing measurements, especially in the Wi-Fi environment, is how do we tell if the methodology that we're using is valid, right? So we thought, how do we validate a measurement methodology? So our view was that there were two requirements that we saw as very important. One is that if there should be no differences in performance, then the methodology should not report any differences, right? So if you run the same thing over and over again, it shouldn't claim that there are differences in those exact same measurements. And then if there are differences, how can you tell if there are differences? Or can you tell if there are differences, and how do you tell? Or in other words, and maybe more importantly, are the differences meaningful? And so, for example, maybe there's some test for statistical significance. And that's kind of the metric I'll use throughout the talk, is some notion of statistical significance. So how do we evaluate this methodology? So step one is there should be no differences if there shouldn't be differences. So the idea is to take the methodology, repeat the same experiment over and over again without doing any changes, and check to see if there are differences. There shouldn't be. And so if there are differences, then that methodology is flawed, right? So that's step one. And this is being done by lots of researchers these days, and Robert just talked about some of them. And then step two is, are the known differences statistically significant? So the approach here now is using the methodology, conduct experiments with known differences in performance, and then if the differences are not statistically significant, that means the methodology might be flawed, or maybe the variability is too large for useful or credible conclusion. And so that's kind of a bit of a different thing. And now, how do you run experiments with known differences? I'll talk about an example of what we've done in that regard later on. So what we started with is, in a cloud computing environment, let's evaluate the methodologies that are being currently used or that were being used at the time to see if they're valid. So a single trial, this is, comparing technique A, B, and C. We've got the three different techniques. We want to compare those. So let's take an example from some of the data that we had access to, very trivially, right? If you happen to run trial, if you happen to run A at this point in time, the blue circle, and then B at this point in time, and C at this point in time, C would incorrectly be shown to be much, much better than B and C. Remember, this is data where we're running exactly the same experiments over and over and over again. They should all produce the same results. If they don't, the environment has changed, right? So very clearly, this is very clearly flawed, but it's still used, right? And it's still widely used. So we're all good scientists. We know, okay, well, you can't do that, right? You've got variability. You have to repeat your experiments, right? You have to do multiple trials. So this is considered among the best practices, probably, you know, up until maybe more recently was, well, sorry, maybe it's still considered the gold standard by most publication standards. The idea is I run multiple consecutive trials of A, multiple consecutive trials of B, multiple consecutive trials of C, and then I compute some metric, say maybe the mean and some confidence intervals or a median and a confidence interval to try to see if these things are similar or not. So what we did was we took the data from this study, right? And the idea is we said, let's imagine that each experiment was considered a different trial. So we do 20 trials of each alternative and we compute 95% confidence intervals, right? So what we're expecting is that we're hoping that if things are similar, we'll see something where the confidence intervals overlap, right? Also, all results here should be statistically similar. If not, and the confidence intervals don't overlap, then that could lead somebody to make an incorrect conclusion about one being better than the other. So if they're not statistically similar, then this approach is flawed. So we took the data, a different set of data. This is CPU performance for US small instances from that same paper. And you can kind of see here, if you were to run your experiments at this point in time, things look quite good. Now remember, what we're doing here is we're comparing two alternatives. They're really the same experiment being conducted over and over again. We're going to pretend, let's imagine that somebody ran one experiment at this point in time here, right? They ran 20 trials, and then right after that, they ran 20 more trials of a different version of the software, right? Now, in this case, it's exactly the same thing running. So if you were to happen to run your experiments at this point in time, things are looking pretty good, and not high variability. Now, I should also point out that it's a very dangerous thing to run some experiments to check for variability, and then to say, oh, let's imagine I checked for variability and this was the set of experiments I ran. I'd say, oh, this environment isn't variable. I don't have to worry about variability. I can just report a single trial, right? You would be completely wrong because variability changes over time, right? The environments change over time. And so you have to, and hopefully this is a lesson that I really want everybody to understand, not this audience, but we need to make this more broadly known, is that variability happens all the time. So if you look at that area, things are looking pretty good. But if we were to compare, that's if you ran two consecutive experiments, things are looking pretty good. But if you happen to compare an experiment that was run at the first point in time with another experiment that was run much later in time, the environments change so much that those are completely different. It's like running on a completely different system is one way to think of it. The environments change so much, you can't make a comparison between those two. Now, the technique though here is the assumption is we're running one set of experiments A, followed immediately by one set of experiments B, so they're close in time. So let's zoom in on this area of the graph. And when we zoom in that area of the graph, we can see here that there is an experiment that's run at 20, we run 20 trials of one experiment A, and then we run 20 trials of B, and those confidence intervals do not overlap. And so this is a flawed methodology, right? So this is scary. And I think it's very scary because the confidence intervals provide a false sense of validity, credibility, and rigor, right? It's like, yeah, these people are doing all the right things. So this must be a credible study. But the problem here is that the environment has changed between trials for A and trials for B. Again, it's like you're running on two different systems. So the existing approaches that I've talked about so far are single trial, multiple consecutive trials. Most existing evaluations use one of these two approaches. So in our paper, we had looked at some papers from the Symposium on Cloud Computing. There were 18 evaluations. Of those performed on public cloud, 7 were single trial and 4 used multiple consecutive trials. this problem is widespread and continues, and Robert just referred to some of those other papers, or at least one other paper that talks about this problem. So in our work, and this was done in 2015, I guess, with regards to Wi-Fi networks, our proposal was to use multiple interleaved trials. Like in the Wi-Fi environment's really nice because we know that things change. We know that they change at very small time scales. And so how do we handle that situation? So the proposal is we run one round where we interleave. We run A, B, C, and then we run A, B, C, and we run A, B, and C. And we do one round, followed by another round, followed by another round. And then we can compute some statistics across those different trials for A and for B and for C. But the key here is to try to expose each round, try to expose them to a similar environment as we can. Now, the one thing that we realized is that, wait a minute, if there was a periodic interference of some sort, so let's imagine something happened with the same time interval that C was run at, then C could be harmed or hampered or maybe even improved in some way that is systematic with respect to the time at which it's run. And so, and likewise, there are results that show that the order in which we run experiments can have a big impact on the results as well, right? There could be caching effects that improve the performance for later executions. So we also propose using something called randomized multiple interleaved trials, where within each round, we randomize the order so that there's a different ordering of each trial or of each alternative that we're comparing. So we're going to examine each of these approaches now to see if they could be used successfully in a cloud computing environment. So again, we took a set of data from the same paper, the data we were able to get get access to. And now what we're doing is we're saying, let's imagine we run A, and then we run B, and then we run A, and then we run B, and then A and B, and on and on. So in this example, we run 20 trials, and we're comparing consecutive times, remember, right? So now they're kind of running approximately at the same time, and we can see in this gray area. So for a lot of this graph, we're seeing that the confidence intervals overlap, which is nice, right? We can't compare something at this time with something at this time, but we can compare that pair of results and that pair of results. But if we look in this gray area, we see some problems. So I'm going to zoom in on that gray area. And we can see here that, again, there's an example here where if I had happened to run my experiments at that point in time, I would report that there's a difference when in fact there are no differences at all, right? Is running exactly the same benchmark over and over again. And we're reporting that, yeah, there's statistically a significant difference between these two. So that's a flawed approach. So if we look at randomized multiple interleaved trials, this is the same data, just now we're randomizing the interleaving of these results. We find that in that gray area, if we zoom in, that these confidence intervals do overlap now, and so they are all now similar as they should be. So with RMIT, we don't see differences when there shouldn't be. It's the only approach we studied to pass step 1 using our methodology. And so what we'll do now is look at step 2, right? So step 2 is, I want to test known differences. So how much variation, so the question is, how much variation is there in the measurements being used? And then the important question is the variation too large for the differences that are being claimed in the work that you're doing or examining? So our approach for this was that let's conduct an experiment where we know what the expected difference is between different experiments. So what we're going to do is we're going to transfer a file of 200 megabytes. And in our case, we're doing a Wi-Fi experiment. So our base case is 200 megabyte file, and the relative size is that's our base case, so that's size 1. And then we make a file 10% bigger, and then 20% bigger, 30% bigger, and 40% bigger. And the expected results is that it should take 10% longer, 20% longer, 30% longer, and 40% longer, right? So the idea is conduct an experiment where you know what the difference should be, and then measure to see if it's actually there or not. Okay, so this is like testing 5 different alternatives, A, B, C, D, and E. And so I'll refer to them as A, B, C, D, and E. And I'm now going to show the results of those experiments. This is run on a 2.4 gigahertz Wi-Fi network. So this is a network that is operated in the university. There are other Wi-Fi networks nearby that may or may not interfere. There are microwaves that may go off and interfere. There are people moving about. There are many devices contending for the same network. Or sorry, not for the same network, for networks nearby. We actually ran this on a separate network. So on the x-axis, we have our different sizes, A, B, C, D, and E, right? So these are the relative sizes. And then in blue, we have 5 trials. In red, we have 10 trials. Green, 15 trials, and purple, 20 trials. And on the y-axis is the transfer time. So you can see with 5 trials, we've got very high variability, right? You can't say anything useful or statistically significant about the differences between those. So you're not able to make any useful claims. As the number of trials increases, as you would expect, the confidence intervals get a little smaller. But even at 20 trials in this environment, it's very hard to make claims about one being statistically different than the other, right? So it looks like the confidence intervals don't quite overlap between the base and something that's should take 40% longer. So those confidence intervals don't overlap, but all of the others do. So this is to say, at that point in time, for those experiments using this methodology, all I can really do is distinguish differences that are 40% or larger. Now, if we have less variability, we ran the same experiments with a 5 gigahertz network. In this case, we were able to control, there were no other 5 gigahertz networks in the vicinity. Wi-Fi environments are quite nice because there's still a high amount of variability due to movement and lots of other issues. And so we ran the same experiment with a 5 gigahertz network, and we could see, again, that more variability with fewer trials. And as the number of trials increases, we get tighter confidence intervals, and we're actually able to distinguish better, different, or more easily distinguish smaller differences. But the message here and the point is that I think it should be part of the experimental design to try to understand what differences can be measured and what can't be measured, and to help the reader to understand that. So some important issues with this type of work, or this type of experimental evaluation, is we have to consider the number of comparisons that we're making. 2 alternatives is very different from 5 alternatives, right? Because each alternative takes some time to run, and as time progresses, the environment can change. The duration of each trial is also important, right? The alternatives we want, we'd like them to be exposed to very similar environments, right? Or at least similar changes in the environment. In a Wi-Fi network, we found that it was very nice if we could run short experiments, because there can be very big changes over very short time intervals. And then, of course, the other big factor is the number of trials that you're going to run. More variability requires more trials naturally. And as Robert pointed out, they've done some work in that area, and they've got a nice, it looks like what could be a very useful tool for helping people to make decisions about how many trials to run. So to wrap up, performance in clouds and many other environments is variable, right? These changes in the environment happen. It's not feasible to know before, during, or after the experiment whether changes happen. And I think this is something I really, really want to emphasize, right? If you do some experiments and you think that your environment is not variable, then I would argue that you're probably wrong, right? And so I don't think you should say, oh, I don't need to account for variability. I think the default should be account for variability always, right? If it doesn't happen when you're running your experiments, that's great. But there's a very big chance that it is happening when you're running your experiments, and that's bad. So I'd like to encourage people to use credible methods, use randomized multiple interleaved trials. And I think this is the other factor I'd like to remind people of, is to validate your performance evaluation methodology. And I just added this while Robert was talking because, you know, my pet peeve is that in all other sciences, one of the most important factors is reproducing other people's work, right? So I think that we need to publish reproducing other people's results. That needs to be a first-class, fully recognized paper, not a special track. It's like, it's just good science. And that's all I've got. Thank you.
Thanks, Tim. Great talk. There's lots of people who are convinced that these are real problems because it's called perf. Can David Daly please unmute and ask his question?
Yeah, thanks for the talk. I really enjoyed that. My question was about, you're trying to control for the noise of the system. What about noise in the actual alternatives that you're evaluating also? We have many cases where software, I work with software, where a software change won't just make something faster or slower, but will make it more variable also. And so you considered the null hypothesis and seeing how sensitive a change you could measure. What about when the noise itself changes from the software?
Yeah, so if I'm understanding, like, so I guess the issue is that I wouldn't presume to be running different versions of the different software to compare over different times, right? So the idea would be, I would take one instance of that software and then run and measure that. I'm not sure if that's, if maybe I misunderstood what you were talking about. Well,
to make it very concrete for myself, say I have a release of my software and I want to compare, is MongoDB 4.4 faster than 4.2?
Ah.
You know, and it turns out maybe that 4.2 is noisier than 4.4.
Got it. Yeah. There's more variability in one's execution than the other, and hopefully you can see that through the measurements, right? If you're using some technique where you're reporting your variability, you would see, oh, it's more variable. And so then that's where the statistical techniques would come into play, right? To see, can you actually make a claim that this new release is faster or is it slower? And I think we just have to accept that there is that's one of the things that I think was useful for us working in Wi-Fi networking, is we have to accept that there is variability, right? And it just means that your claims are limited, right? So maybe you can't make a claim that it's improved performance by 30%, you know, because the variability is too high. We just have to accept that and live with it. And I think part of the problem is that people aren't willing to do that.
Yeah, thank you. We're living with that every day.
Okay, thanks. Maybe one more question by Andre Bondi. I think you're muted.
My question is, does your work underscore the need for profiling of the software so that one can expose problems while eliminating the noise? And I don't just mean code profiling in the sense of seeing how many times this, that, and the other is executed, but also picking up where the delays might be. If there, for instance, if there are system calls that involve interactions with other processes and so on.
Yeah, so I think finding the root causes of variability is a completely different and much harder problem. I think I'd just like to get people to understand that there is variability and to deal with that. It's certainly not going to hurt. I guess you have to consider the fact that, you know, if you add profiling, that may increase variability as well.
So one would have to do it in a test environment rather than in a production environment, if at all possible. Because if you're trying to show that A is better than B, then you have to have some way of controlling.
Yes, yeah, you know, and we're trying, you know, people are, and I guess that's part of the issue, right? Is that when you're in a cloud environment, you're giving up control. There is no control, right? You know, because at any point in time, the vendor can do whatever they want, right? And you may or may not be aware of it.
It's a bit like the problem with agricultural testing. Is this breed of corn better than that breed of corn, and how do you
absolutely
how do you make an inference about that?
Yeah. No, I think, you know, and these are techniques that people in other fields have to deal with all the time, and you just have to be able to accept that. Yeah, you know, it looks like maybe there would be 30% improvement, or we'd like to think there's 30% improvement, but the variability is too high to make that conclusion.
How do you overcome reluctance to replicate?
Sorry, repeat the question again, sorry.
How do you overcome, well, actually, this is an industrial question. How would you overcome a reluctance to replicate? I've seen a lot of that.
When you say reluctance to replicate, you mean reluctance
replicate performance tests, replicate experiments, or replicate measurements.
Yeah, do you mean the reluctance to publish work that replicates work? Or
no, I mean a reluctance to actually run an experiment more than once, or take more than one measurement.
So
see Robert nodding his head vigorously.
If you're unwilling to do that, I don't know what you can do, right? How can you help people like that?
I know.
I'll just step in and say, I mean, my opinion is that some of this needs to come from sort of the program committee level, right? Like, we need to, in program committees, at least give papers a hard time and maybe not accept them if they don't do this when they really need to be.
I'm a little older than some of the people in this group, but there was a time where papers did get rejected for, I could not reproduce this in my lab, right? There's not enough detail here to reproduce this paper, reject.
Tim, if I may ask one small question, I don't know if there's time, but maybe I can take it up later. I don't know.
Is there time?
Maybe a short question, sure.
I mean, it's just concerning, in old days, resources used to be limited and we used to test on
Abhishek, your sound
variable infrastructure where you can get meaningful performance results. Sorry, are you able to hear me okay?
No. Can you type your question maybe?
Yeah, it's too long to type. Is it okay now? Is it better?
Sure. If you like, we could do a private one-on-one session later on if you like.
Yeah. I think that it's fine. Yeah. Sorry about that. Yeah.
No problem.
Okay, thanks everyone. Those were great talks, and I think there's lots of people who want to keep talking about this, really, from what I've seen in the comments. So we should definitely use the Slack and the breaks that we have to keep the discussion going. Thanks.
Thank you.